Hi everyone. This is the first video in Module 1 of this series, and we're going to be talking about representing numbers in Module 1. And in this particular video, we'll be talking about integers. Now, when we think about that, intuitively speaking, representing integers, we're just talking about whole numbers, right? A number that's not a fractional value is an integer, and that's pretty straightforward. It certainly seems like there shouldn't be too many surprises when we start trying to represent these, but as we'll find out, in a computer system, there are some things we have to watch out for, and we need to know exactly how these numbers, how these integers are being represented in a computer system. Now, if you happen to be following along in the book, Computer Systems, A Programmer's Perspective, this is where we'll start covering material from Chapter 2 in that textbook. Specifically, I'm using the 3rd edition. So we've all heard that in a computer system, everything is ones and zeros, right? Everything is bits. And each bit is either a 0 or a 1. All a bit is a single binary digit. So we're talking about a base 2 numbering system. And so all we have are 0 and 1 to work with. And we can encode or interpret sets of bits in various ways. Right? We have these ones and zeros. How we interpret them is up to us. And so computers can use these bits to determine what to do. Right? We can encode instructions in binary, and we can represent and manipulate numbers, sets, strings, etc., etc., etc. This is why something this simple turns into all these wonderful and complex things that computers do. It all rests on storing and interpreting information as a series of zeros and ones. So why bits? Why are we using zeros and ones, right? Why not use decimal? Why not use something else? Well, because a computer system, of course, is going to be implemented electronically, and it's easy to store zeros and ones with what are called bistable elements. We can also reliably transmit these, what are often referred to as logic levels as well, right? Off or on, 0 or 1, on noisy and inaccurate wires. Now, the way that works is we just define certain ranges of voltage to equal our zeros and ones. So we might say, hey, between 0.0 volts and 0.2 volts, that'll represent 0. And then when we get up to somewhere between 0.9 and 1.1, so around 1 volt, is a 1. And so as you can see from this diagram, we can actually have some play, right? We don't have to have it actually right down at 0 to represent a 0. We can have a bit of a range. And so if I'm transmitting information over a network wire, right, or over radio waves, etc., I can allow for some noise. It's okay if it fluctuates a little bit as long as it stays within that range. That means 0, and the same applies for ones. So using zeros and ones gives us the ability to easily store and reflect those values in an electronic implementation, and it also gives us some play. It allows us to use wires in the real world to actually transmit this information because a little bit of noise isn't going to mess up our data too much. Now, a great example of how we're encoding things and how we can interpret them kind of however we want is to take a look at the different ways that we can encode and interpret a simple byte. Now, a byte is just 8 bits, right? So I take 8 ones or zeros, put them all together, that's a byte. By the way, it's something, piece of terminology that you'll hear. And I think it's kind of cute, is that half a byte, so 4 bits, is actually referred to as a nibble. So when we start talking about different base numbering systems, we'll often reflect that. We'll often refer to those by using a little subscript. So binary will have a little subscript 2 at the end. Decimal is a base 10 numbering system, so that'll have a little 10. Hexadecimal is base 16, so that'll have a little 16. All right, so we want to keep that in mind, keep an eye out for those things because that's going to tell you what base numbering system we're using. So 8 bits, clearly enough, in binary, that's going to be anywhere from 8 zeros to 8 ones. Now that translates in decimal to 0 to 255. In hexadecimal, it's 0 to FF. Now, something to mention about hexadecimal, if you haven't messed with hexadecimal too much before, it's a base 16 number representation, as we can tell from the little subscript. And so that's going to use the characters 0 through 9 and A to F, right? Because with a base 16 numbering system, I have to have 16 individual digits. Now, with binary, it's base 2, so 0 and 1 gives me all the digits I need. With decimal, 0 through 9 gives me 10 individual digits that can go in any of the places. That's my base 10. With hexadecimal, we've got to expand beyond what we typically think of as numbers because we need 16 different values. Now, another note, when we're using C, if we wanted to write FA1D37B in base 16, right, if we want to reflect that hexadecimal value in C, we would put a 0x in front of it. That's not a capital O, the letter, that's a 0. So 0, then lowercase x, followed by the digits. That tells the compiler, oh, this is hexadecimal. And something else to note is it doesn't matter whether it's capitalized or in lowercase, right? We know that it's going to be a hexadecimal value, so it's just looking for the letters themselves and translating those to the appropriate values. Now, this table to the right shows you the correspondence between the hexadecimal values, decimal values, and binary values of 0 through 15, if we're speaking in decimal, right? And so we can just see that counts up, and once we get into, say, 10, right, that's going to correspond to A in hexadecimal. 11 is B, 12 is C, etc. Another thing to note, because we're going to need to sometimes, even just by hand or in our head, convert back and forth between specifically these numbering systems, right? Binary, decimal, and hexadecimal are all very, very common, so it's really good to be able to go back and forth between them. Note that every hexadecimal digit corresponds to a nibble in binary, so that makes it a little easier to deal with converting back and forth. So if I see FA, like in the example to the left, I know that those first 8 bits, right, are going to be the nibble for F, which is 1111, and the nibble for A, which is 1010. And we can move on through that way, and it's just a one-to-one correspondence between all of these numbering systems. Now, how many bytes we use to represent various data types are, when all is said and done, they're going to be platform specific. But there are some typical values that this table lays out for you. So, for example, whether we're dealing with a typical 32-bit system, a typical 64-bit system, or specifically an x86 64 system, a character is generally going to be 1 byte long. A short will be 2 bytes, an integer 4 bytes. Eventually, we get into some stuff that is different, though, and so we're going to want to keep that in mind. A long, for example, on a typical 32-bit system, that is also going to be 4 bytes, whereas on a 64-bit system, it'll be 8 bytes. Floats are typically 4 bytes, doubles are typically 8. Pointers on a 32-bit system will be 4 bytes as opposed to 8 bytes for 64-bit systems. So this shows you that, A, you have to be aware of what you're coding toward, right? You need to be aware that different types of system will have different byte lengths for these various data types sometimes. So we need to be aware of that as we move forward. Now, another thing that we're going to see a lot of when we're dealing with computer systems is something called Boolean Algebra. This was developed by George Boole in the 19th century. It's just an algebraic representation of logic. We encode true as 1 and false as 0. So you can see this applies to computer systems very, very well, since that's what we're using to represent basically everything we need to represent in a computer system. We're using 1s and 0s. So we have various logical operations that we can perform. We have the logical AND, right? And we see these truth tables here. So when both A is 1 and B is 1, that's going to evaluate to 1. And when 0 and 0, it's 0. And when one or the other is 0, it ends up being 0. So we can track through these truth tables what these operations do. For an OR, It's going to be 1 when either A or B is 1, and we can see that in the table here, right? If both inputs are 0, then the output is going to be 0. If either of the inputs is 1, then the output ends up being 1. A not is just a negation, right? So when the input is 0, the output will be 1. When the input is 1, the output will be 0. And our exclusive OR, which some people find a little bit confusing, but it's not too bad, trust me. When either A or B is 1, so when either input is 1, but not both, this will be a 1. So if both inputs are 0, it'll be a 0. If one or the other input is 1, then it'll evaluate to 1. And if both inputs are 1, it'll evaluate to 0. You can think of a real-world example being, say, a couple of light switches that are at opposite ends of a really big room, right? We set those up so that if both are up, the lights are off. If both are down, the lights are off. And then when you toggle it so that they're in different positions, the lights would be on. And this is what allows you to walk up to one or the other of those switches and just change the state of that switch. That's going to change the state of the lights. Right? We don't want to have to flip one switch on and then walk through the dark all the way through a room to flip the other switch on in order to turn the lights on. So we have it set up with an exclusive OR. So that's a real world example of what an exclusive OR does and how it operates. Now, we can apply these operations in a bitwise way to bit vectors, right? We don't have to just have a single 0 or 1 and a single 0 or 1. We can take whole big vectors. So in this examples, we see whole bytes. And when we apply these operations to these bytes, we just apply them bit by bit. So in the case of the AND over here on the left, let's start at the left and move to the right. 0 and 0 is 0. 1 and 1 is 1. 1 and 0 is 0, etc. and so on. We can look at the same thing with the exclusive OR here. 0 exclusive ORed with 0 is 0. 1 exclusive ORed with 1 is 0. 1 exclusive ORed with 0 is 1. And we just work our way through each pairing in these two bit vectors and just apply the operation separately to each pair of bits. All of the properties of Boolean algebra apply to bit vectors. Now, a really nice example that can show us both using binary digits to represent things other than simple numbers, right, and also shows us the utility of some of this Boolean algebra, some of these bitwise operations, has to do with representing and manipulating sets. So let's say that we use a bit vector to represent subsets of some original set. Now in this example, we'll just use bytes, right? So we'll use 8-bit bit vectors, and our original set will just be 7, 6, 5, 4, 3, 2, 1, 0. Right, just the digits between 0 and 7 is our original set. And if I want to reflect subsets, I can just use a 0 in a bit vector to indicate that that corresponding element in the original set is not part of my subset, and a 1 to indicate that it will be part of my subset. So if I use 0, 1, 1, 0, 1, 0, 0, 1, I can now use that to represent the subset containing 0, 3, 5, and 6. If I use 0, 1, 0, 1, 0, 1, 0, 1, that will represent the subset that contains 0, 2, 4, and 6. Right? So simple enough. A 1 means that it's part of this particular subset. A 0 means that that element in the original set is not part of this particular subset that I'm representing. So there we go, using simple binary digits to represent something that's beyond a simple number, right? We're going to apply it and interpret it to manipulate these sets. Now, how do we pull Boolean algebra into this? Well, we can use those Boolean operations to indicate what we're doing. So think back to set theory, the intersection, right? What's the intersection of these two subsets? Well, those are the elements that are present in both subsets. So I can just AND those two bit vectors together and find out that, 0 and 6 are the elements that those two subsets have in common. The union is the combination of all the elements within either or both. And since it's either or both, I can use a simple OR, right? So if an element is in one or the other, or it's in both, it will be part of the union, and we see that reflected here. the symmetric difference, right? So what is present in one or the other, but not both sets? That's the definition of an exclusive OR. So I can exclusive OR these two bit vectors together to find the symmetric difference. And if I want the complement of one or the other, right, I can just use a simple not and pull out the elements from the original set that are not present in the subset. So we can, again, represent with simple binary digits something a little more abstract, a little more complex like sets, and we can use Boolean algebra very simply to perform basic set operations. Now, something that's very nice for us when we use C is all of these bit level operations are available in the C language. They apply to any integral, so any integer sort of data type, so longs or ints, shorts, characters, unsigned. We view the arguments as bit vectors and then just apply the operations bitwise, just like we have been. So let's say we have a char, or a character data type. If we not, now it's okay, we can represent these in hexadecimal because we're going to apply things after we convert to binary. So if we have 41 hex and we not that, well, we just turn that into binary, and that ends up being 0, 1, 0, 0, 0, 0, 0, 1, right, in base 2. We take the not, and we're just flipping the bits. When we do nots, the same thing applies to 0 hex. That's going to turn into FF because we're just going to flip those zeros to a bunch of ones. We can also do the other operations. 69 in hex, if we AND that, a bitwise AND with 55 hex, we'll end up with 41 hex, and we can see how that works. We convert those to binary, go bit by bit, 0 and 0 is 0, 1 and 1 is 1, 1 and 0 is 0, etc., and so on, and we end up with our output. Same thing applies when we're doing an or an exclusive OR for that matter. These all apply by we simply just take whatever we put into the function, we represent it in binary, and apply the operation bit by bit, and we get the correct output. Now, something that can be a little confusing is when we deal with logical operations in C versus these bitwise Boolean algebra operators, because they're very similar. When we deal with a logic operation, instead of a single ampersand for AND, we're going to use a double ampersand. Instead of a single pipe for OR, we'll use a double pipe. For not, instead of a tilde, we'll use an exclamation point. And these operate differently. These are not bitwise. They're going to view a 0 as false and anything that's non-zero as true. It's going to take the entire thing as opposed to breaking it down into the bits and applying things bitwise. They take the entire value. If it's 0, it's false. If it's not 0, it's true. And these will always return a 0 or a 1. It's a simple true-false evaluation, not a bitwise operation. Now, one nice thing that these do for us is they allow for early termination. What does that mean? Let's say I'm going to AND a bunch of stuff together. Now, I know, based on how AND works, that all of the inputs have to be true in order for it to evaluate to true. So if I get to the third out of 15 different things that I'm ANDing together, and that third input evaluates to 0, well, I know the entire operation is going to be 0, so I don't have to process the rest of them, and the compiler's smart enough to do that. It's going to go through, it'll evaluate, oh, the first input is true, I'll move on. The second input is true, I move on. The third input is false. Okay, now I know that the entire expression will evaluate to false, so I'm not going to evaluate the rest of the inputs because I don't need to. I know what the output's going to be. So some examples of this, if we do a negate, right, if we do a not on hex 41, we're not flipping it around like we did on the last slide. We're not going to come out with that value that we came out with on the last slide. It's just going to be 0, right? It's 41 is a non-zero thing, so that's true. And when we not that, it becomes false, and so that's a 0. If we do a not of 0, we don't get FF like we did last time because we're not doing this bitwise. A logical not of 0 just evaluates to 1 because 0 is false, therefore it comes out true. If we double not, right, so we apply not to 41 and we get a false or a 0. Then we apply not to that 0, we get back a 1, right? So these are simple logic operations. They don't go bitwise. It's just true and false. And we can see that again with hex 69 ANDed, logical ANDed with hex 55. We're not just getting a new value, we get 1 because we have two trues ANDed together. That's a true. 69 ORed with 55, also we get a 1, right? We get the same result out of both of those logical operators because we're simply evaluating true and false as the inputs and a true or false as the output. Another trick that we can use, which is kind of cool, is with pointers to avoid null pointer access. Don't worry about what that means yet. We're going to get into it when we get into memory management, but we can use this little trick just using a simple logical AND to avoid something called null pointer access, which is something that will cause us problems. And like I said, we'll be seeing that in later chapters. So I do want to caution you really quickly about this. Be careful for the difference between these logical operators and the bitwise operators. Because again, it's easy to confuse them. The double ampersand versus the ampersand, double pipe versus pipe, they look very much the same. It's an easy mistake to make. And even when you go back and look over your code again, it's easy to miss the difference between those two. It's one of the more common oopsies in C programming, is using the wrong kind of Boolean operator, and so all of a sudden your program is doing things that it really should not be doing. So let's continue on to some more basics and take a look at shift operations. We've got left shift and right shift, so let's go ahead and cover them one at a time with a couple of examples of each. In a left shift, we use this double left arrow looking thing to indicate that we're going to take bit vector x and shift it left by y positions. Now this is pretty straightforward. We just throw away the extra bits on the left and fill with zeros on the right. So let's take a look at a couple examples of that. If our argument x is 0, 1, 1, 0, 0, 0, 1, 0, then left shifting that by 3, that 3 would be the y in our previous example. What we do is we just drop off the top 3 on the left of the argument. So the 0 drops off, the 1 drops off, the 1 drops off as we shift it past the 8 bits that we have to work with. So what we're left with is 0, 0, 0, 1, 0. And as we've shifted each place, we fill with a 0 on the right. So we end up with these 3 zeros in the least significant digits. So pretty simple, right? We just move over by 1. We drop the 1 on the left and we add a 0 to the right. We move again, we drop the most significant digit on the left, we add a 0 at the right, and so on for as many times as we're going to shift. We can see this in action again with the second example. If our argument is 1, 0, 1, 0, 0, 0, 1, 0, then when we shift 3 places, we drop off that 1 and move everything to the left and then add a 0 to the right. We drop off the 0, move everything to the left and add another 0 to the right, drop off that other 1, move everything to the left 1, add another 0 to the right, and what we end up with is our 0, 0, 0, 1, 0, 0, 0, 0. Very straightforward. We just move things over, assuming we only have the 8 bits in this example to work with. Then as we shift to the left, each digit that gets shifted outside of that 8 bits, so each one on the left drops off, we fill with zeros on the right. Pretty simple. Now with right shift, things get a little more complicated. It's just this double right arrow, so that's easy enough. We're just going to shift bit vector x to the right by y positions, and we throw away the extra bits on the right. So for the most part, it works exactly the same, but the question is, what do we do with the left side? And so we have 2 different kinds of right shift. We have a logical shift where we're just going to fill with zeros on the left. So that one's a logical right shift is very similar to the left shift that we already went through. We shift things over, digits drop off on the right, and we fill with zeros on the left. And again, we can see that with both of these examples. Our logical right shift by 2, when we use our first example, the 0 on the right drops off and we fill with a 0 to the left. The 1 that's now left at the right drops off and we fill with another 0 to the left, and we end up with our result. Same thing with the other example. The 0 that we have all the way at the right drops off, and we fill with the 0 to the left. Then the 1 that is now all the way to the right drops off. We fill with the 0 to the left, and we get our result. Now, that's different when we talk about an arithmetic right shift. Now, with an arithmetic right shift, we're still going to drop off the bits on the right, but we're going to replicate the most significant bit on the left. So this actually ends up being the same for the first example, right? Because our most significant bit is a 0 in this first example. So as we shift that 2 to the right and we do an arithmetic shift, we drop off the 0 and fill with a 0 on the left, because that most significant bit in our argument is a 0. That's why that one's a 0. With a logical shift, it's a 0 no matter what. With an arithmetic shift, we replicate the most significant bit. We do the next shift, right? So our second one, the 1 that's at the end now drops off, and we fill on the left with another 0. But that's going to be different with the second example, because notice we have a 1 as our most significant bit in this example. So, first time we shift, the 0 drops off, and we fill with a 1 on the left. Then we shift again, the 1 drops off. So when we shift for the second time, the 1 drops off, we fill with another 1 on the left. So, when we talk about a right shift, we have to be careful about, are we doing a logical shift where we just fill with zeros on the left no matter what? Or are we talking about an arithmetic shift where we replicate the most significant bit on the left? So that's a very important thing that can lead to a lot of confusion, and we want to keep it in mind. Now, we also have some undefined behaviors that we want to keep in mind. We can't shift by greater than the word size, right? So if my argument is 8 bits, or if let's say I'm on a 32-bit system, I'm using 4-byte words, I can't shift by more than 32, right? I can't, or even equal to 32, right? I can only shift by 31 or less on a system that has a word size of 32 bits. And I can also not shift by an amount that's less than 0. I can't shift by a negative amount. That doesn't just go the opposite direction. That is undefined behavior. So now we can finally get into how we actually encode integers. Now we've got a couple different mathematical expressions here that just show us how to convert from binary to the value of an unsigned integer. And this b2t of x is how we convert to 2's complement. Now, this looks a little scary, but it's not bad. We have w is just the length of our input, right? So however many bits we have to work with, that's the value for w. So we'll go from place 0, which is the least significant bit. Okay, so that'll be the one to the right, up to w minus 1, which is, of course, going to be the most significant bit. Now, to go to unsigned, we just do the value of x, right, the value of the input vector at that place times 2 to the I. Now, what's that 2 for? It's because we're dealing with binary. So we're dealing with a base 2 numbering system. So we take the digit that's in that place, multiply it by 2 to the I, right, to the number of the place that we're in. That's what we get. And this works exactly the same as it does in decimal. Except in decimal, we would use a 10 instead of a 2 because decimal is base 10. So all we're taking is the value at the place that we're looking at times the base raised to the place. So in the ones place, we would just have the value of the ones place times 2 to the 1. In the 0 place, the least significant bit, it would be the value in the zeros place times 2 to the 0, etc. and so on. We just sum up those evaluations, and that gives us our output. Now, 2's complement works pretty much the same way, except all we've done is instead of going from I equals 0 up to w minus 1, we'll sum from I equals 0 up to w minus 2. Now what that does is it leaves the most significant bit, because in 2's complement, that's the sign bit. Right? So it has the same weight, but that weight is negative, and this allows us to reflect negative numbers. So this part of the function over to the left here, this is just saying, look, take the value of the most significant bit, multiply that by 2 to the power of the place of the most significant bit, and that's going to be negative. That whole thing is going to be negative, so that's what does that for us. Now, let's put that aside for a second, and if you don't quite see how that's coming together yet, don't worry about it, because we're going to go through a couple examples. So refer back to these functions as we do that, and you'll see how it all comes together. So let's start by taking a couple short integers. Okay, one will be positive 15,213, and the other will be negative 15,213, and let's see how this all works. So let's start with x, and our value of x is 15,213. Now let's go over and look at the binary, though. Now, recall that in C, a short is 2 bytes long. That means we have 16 bits to work with. So in our functions, the value of w will just be 16. So a short is going to be, we can have negative numbers, so we're going to be looking at the b2t of x. That's our 2's complement, right? So we'll start with the least significant bit, and that has a 1 in it. That's the place where I is equal to 0. So x sub 0 is 1. We multiply that by 2 to the 0 power, and anything raised to the power of 0 is 1. So far we have a 1. Now we keep walking through our i's as we go through this summation. All right, so we move over to the I equals 1 place. Now there's a 0 there, so the x sub I evaluates to 0. We multiply that by 2 to the 1. Well, that whole thing comes out to be 0, so we're still sitting at 1 for our total sum. We move over to the next spot. I equals 2. The value of that is 1 times 2 squared. That's 4. We add that in. Now we're up to 5. And so on and so forth. We just walk through the binary doing this for each bit. And eventually we get all the way through. We get to that most significant bit, and we're going to multiply that by this part of the function that's over on the left that indicates what we do with the sign bit. Now that's a 0. X sub w minus 1 evaluates to 0, so that whole part is equal to 0. And we end up with a positive 15,213. We do exactly the same thing with y, right? We go down, we start the I equals 0 place has a 1, so 1 times 2 to the 0 is 1. The I equals 1 place has a 1. 1 times 2 to the 1 is 2, so we're at a total of 3. We keep walking our way through, but eventually we get to the point where we get to that most significant digit. Now, once we've gotten all the way up there, we're actually sitting at a value so far for this whole sum of 17,555. But remember, that most significant digit has a negative weight. So there's a 1 in that I equals 15 place. That evaluates, when we multiply that by 2 to the 15, what we get there is 32,768. But remember, that's a negative value. So when we take 17,555 and subtract 32,768 from it, we end up with our negative 15,213. Now, in case that seemed a little bit overwhelming, this is a representation of that same process that might be a little easier to wrap your head around. We've got the same numbers, right, and the same weights that we've been applying, but we've just put it out here in a table so that we can kind of see how this works. So for each of the examples, we have the least significant bit up at the top, and we work our way down to the most significant bit, and we just multiply those by the weight of each place. Then we just add up the columns to the right to get to our final answers. Now, the way all of that works can give us some information about like some minimum and maximum values, depending on whether we're using unsigned or 2's complement integers. So, for example, we'll use u min for the minimum unsigned, right? And that's just going to be 0 because unsigned, we don't have negatives to deal with, so it's going to be 0, and that'll just be a whole bunch of zeros in the bits. U max, because we don't have that negative weight on the most significant, right? This is all positive weight, so our unsigned maximum is just going to be all 1s, and mathematically that's going to break down to 2 to the power of w, and remember w is basically our word size, right? It's how many bits we're dealing with, minus 1. All right, so we can always, depending on what word size we're using, we can always easily figure out what is the range of unsigned integers that I can actually represent on that system, given that word size. We can do roughly the same thing with 2's complement values. T min, right, our minimum 2's complement value, remember, we have negative weight on that most significant bit, so that'll be a 1 followed by a bunch of zeros, however many we have. Mathematically, that breaks down to negative 2 to the w minus 1. T max, our maximum 2's complement value, we have to leave the most significant bit as a 0 because remember, again, that has negative weight. So we don't want any negative weight in our maximum value, right? We don't want to subtract something out of it. So we leave the most significant bit 0 and fill the rest with 1s. That's going to be 2 to the w minus 1 minus 1. Some other values. For 2's complement, it's interesting to note that if we do just fill everything with 1s, if we just have all 1s in a 2's complement value, that will always evaluate to minus 1. Okay, that will always evaluate to a negative 1. And this table down here at the bottom, I won't go through it specifically, but it just shows you decimal, hexadecimal, and binary representations of these various interesting values for a word size of 16. So pause the video, work your way through that, make sure you understand those. Now, since all of these values are determined by the word size, they're going to be platform specific, right? So my maximum unsigned integer on an 8-bit system would be 255, and on a 16-bit system would be 65,535, etc., and so on. It gets bigger the larger the word size I have to work with. The same applies for the 2's complement maximums and minimums, right? The unsigned minimum is always 0, so that doesn't change based on word size. But the unsigned max and the T max and T min all change based on how many bits I have to work with. Now, one nice thing that C does for us is if we include limits.h, this declares constants, right? So long max, long min, unsigned long max, we've got a bunch of different constants that'll take care of for us. And because those values are platform specific, we don't have to go and calculate those ourselves, right? We can do that to make things a little more portable, and that makes life a little easier for us. We also want to keep in mind a few observations, and if you go back through the mathematics and run through some examples, you'll see why these work this way. But the absolute value of T min is always going to be equal to T max plus 1. All right, so if my T max is 127 in an 8-bit system, then the absolute value of T min will be 128. And of course, it's 2's complement, so it'll be negative. So we can figure out from T max what our T min will be. We can figure out from our T min what our T max will be. And we'll get into some of what this does to us when we start doing operations on integers in future lectures in this module. But that's an observation that we want to keep in mind because we're going to be delving into why these observations work as we move through more material. Another thing to note is that our unsigned maximum is always going to be 2 times the 2's complement maximum plus 1. So for an 8-bit system, again, we take our T max, which is 127, multiply that by 2 is 254, add 1, we get to 255, which is our unsigned max, and that works no matter what word size we're dealing with. So we won't get into exactly why those observations hold true just yet, but we want to keep them in mind. And we'll find out in later lectures within this module exactly why that is. Now, let's just finish up this lecture with some observations about signed and unsigned numeric values. We have some of them that are equivalent. All right, we have the same encodings for non-negative values, whether we're using unsigned or 2's complement. You can see those highlighted here in green. Right? 0, 0, 0, 0 evaluates to 0, whether I'm using unsigned or 2's complement. That holds true for any positive value. They don't start changing until we start bringing the most significant digit into play. That's when they diverge and we start getting different values for 2's complement and unsigned. We have uniqueness. Every bit pattern represents a unique integer value, and now that's within a certain type of encoding. So when we're talking about unsigned integers, every bit pattern represents a unique value. You're never going to find a bit pattern that means both 7 and 15 when we're talking about unsigned integers. And the same holds true for 2's complement. If we're talking about 2's complement, each bit pattern represents a unique 2's complement integer. That also goes the other way. Each representable integer has a unique bit encoding. So once again, if I'm talking about unsigned, when I am given a 10, I know that that's going to go to unique encoding. It's not going to be the same encoding as another unsigned integer. Finally, we can invert these mappings, right? We can go both ways. So given a bit pattern, if you say, look, this bit pattern represents a 2's complement integer, I can go figure out what the value of that 2's complement integer is. I can also go the other way. Given a 2's complement integer, I can go the other way and figure out what the unique bit pattern is that represents that 2's complement integer. And that does it for our first lecture on Module 1, which is on representing numbers in computer systems. We'll be continuing Module 1 in more lectures, but from this lecture, what I'd like you to take away from it is to be able to explain what a bistable element is and why we end up using binary because of bistable elements. Be able to perform simple logic operations, both bitwise and the logic operations, so both the single ampersand and the double ampersand stuff. Make sure you know what the difference is. Be able to perform shift operations, and keep in mind that while left shift is pretty straightforward, we do have both logical and arithmetic right shifts that we got to be aware of which one we're using because they operate in slightly different ways. And make sure you can explain integer encoding rules and the numeric ranges of both unsigned and 2's complement integers based on word size.